So coming from you all the way back from 2017, this is the Intermediate Math Olympiad Maclaurin paper for the easier groups here. It's 6 questions, 2 hours, 10 marks per question for a total of 60 marks. Got to present all working and stuff like that, it's all marked. So even if you don't get all the way to the answer, you can still pick up some marks. I would consider practicing on Hamilton and Cayley papers, though if you're practicing Maclaurin's all the way back to here, like I am, you probably don't need to do any more of these as well. But anyway, let's get straight into it. So question number 1. We've got a semicircle here, radius r, so r goes this way as well, and this way as well. Radiuses meet tangents, which are what these are here, as you can see, at 90 degrees. That makes this shape also have a 90 degree there because of 360 minus 3 lots of 90, which makes this a parallelogram, which makes this the same length as this, and this the same length as this. So we've got lots of r's going on here. And if you wanted to, you could label this length as b minus r and this length as a minus r as well. And there's a few things you could try here. You could try some Pythagoras that will give you some very nasty expressions. The key here is thinking about area. So what we can say is the whole area of this shape is a half times a times b, which is cool, but it's also this square, r squared, plus this triangle, which is a half times this, plus this triangle, which is a half times this. And this doesn't immediately seem good, but when we double everything, we see, okay, well, there's lots of r's, a's, and b's, which is good, because that's what we have here. And also, these r squareds all cancel, and that's when you know you're onto the right track. 2 ways to finish this from here. Either just factorize out the r straight away and divide, and then this is r over 1. So what I can do is I can flip r over 1 over to make 1 over r, while flipping those two over as well. And then of course I can just say this is a over ab plus b over ab, which would cancel down to 1 over a plus 1 over b. Or you can go back to here and you can say, well, okay, instead of doing that, I'll divide both sides by ab, because that will give me 1 over here equals r over b, because the a's will cancel but the b won't, plus r over a for the same reason. And then of course factorize out the r, and then instead of dividing by this thing, which will make a mess, just divide both sides by r and we'll end up with the same expression as well. Good. Question number 2. This question annoyed me a little bit because I got an answer, was happy with it, thought it was right, and then the mark scheme had a different answer, and it took me a few minutes to notice that the mark scheme, in the worked solutions, the picture in the mark scheme looks like this, whereas the picture in the original question booklet looks like this, and you'll notice there's an extra dot included in this question. So we won't be doing the mark scheme's weird interpretation of this problem, which is completely different and has a different answer. We'll be doing the actual question and getting the actual answer to this actual question. Thank you very much. Also, what the mark scheme did is it talked about choose functions, and this Olympiad is designed for Year 11s, so I didn't really want to use choose functions because Year 11s, that's not part of the Year 11 scheme. So what I did instead was just talked about combinatorics only. And what I decided to do was say, okay, there are 2 types of triangles here that you can make. You can either make triangles that fit in one quadrant, or you can make triangles that fit an entire half. And triangles that fit in one quadrant only use dots from 2 branches, and triangles that fit in a whole half use dots from 3 branches. So okay, you can either have triangles that look like this, or that look like this. And I counted those separately. So I said, let's first consider triangles that only use dots from 2 different branches. How many of these are there? Well, what you do is you say, well, let's make this the branch that has 2 dots on it. And we'd say, well, there are 4 choices for our first vertex, and 3 choices for the second vertex. So you choose this one, you only have 3 left. And then you have to choose a vertex from up here, and that's another 4 choices. So it's 4 times 4 times 3, except for these 2 choices here, if you take this dot, say, and that's from your 4 choices, and then you take this dot from the 3, that's the same as taking this dot and then this one. So we'll do this times this times this, and then divide it all by 2 to find how many triangles there are. Except that's only looking up in this quadrant, and it's using this branch as the one with 2 vertices. So now we double that to find how many use this branch twice. So double it and then times it by 4 to get all of the options in all 4 quadrants. So in ending up, we times that by 8 to find this many triangles that use 2 dots on one branch and 1 on the other. So just make sure you followed that logic there to times by 8. It's because there are 4 quadrants, so times by 4, but you could also take 2 vertices here instead of here, so times by 2 as well. Okay, now what about triangles that use 3 branches? Well, this is slightly easier to count. We just have 4 choices for this branch, 4 choices for this branch, 4 choices for that branch, and there's no complicated divided by 2 or anything. We do 4 times 4 times 4, which is 64, and then of course there are just 1, 2, 3, 4 sections we could rotate this triangle into, and so we times that by 4 to get this, and then we add the answers together to get our final answer. Good. So yeah, that's the correct one. Question number 3 then. This is a really nice question. The first thing to know is, if you're looking at quadratics, this is a quadratic. I've given it away already. But if you're looking at things with to the power 4 and to the power 2, firstly I'll just rearrange these so the m's are on one side and the n's on the other. This is a quadratic, right? If you see even powers like this, if you want to, you can write this down. Make the substitution m squared equals x, and then this becomes x squared, and this becomes x, and it's just a quadratic. So, okay, what can I do to quadratics? Well, I can factorize. You can try factorizing this, but it's not fun. Or you can complete the square. And completing the square is an incredibly useful thing that just magically seems to solve problems somehow. And it only takes 10 seconds to do it if you're good at it. So I just looked at this and I thought, well, factorizing is hard. Completing the square might not be helpful, but it only takes 10 seconds. So I'm just going to do it. Right? I'm just going to halve this number and take away the square, halve this number, take away the square. And because this is 441 squared, and this is 16, magically all of these numbers just disappear, which is incredible. Right? And notice how I can complete the square even though it's not a quadratic, because it is really. Because this squared would make m to the 4, and then you'd have minus 21m squared minus another 21m squared, and then this just makes this number here, so that's why we take it away. So yeah, that's fine. And now it's easy to look at this bit now and say, well, okay, now this thing needs to equal this thing, except of course we're squaring things, so just be really careful. If this thing was, say, 5, then sure, this thing could also be 5 to make 5 squared equals 5 squared, but this thing could also be minus 5 to make minus 5 squared also equals 25. So we also need to check this equals negative that. And now, of course, you could check this equals negative that, but that's just the same as this times both sides by minus 1. And you could also check negative this equals negative that, but that's just this case, the whole thing times 1 minus 1. So we just need to check these two cases. Let's do this one first. Add 21 from both sides and take away n. Can you find two whole numbers that have a squared difference of 17? It's not too hard to find 9 and 8. It takes a little bit of searching. Now, of course, there are plus minuses here because these are all squares. So minus 9 all squared minus 8 all squared is just the same as 9 squared minus 8 squared. So there are how many combinations here? Well, there's plus plus, plus minus, minus plus, minus minus. So there are 4 solutions to that. Now looking at this one, we can deal with this like this. And now we all know the 3, 4, 5 triangle, right? So m is 3, n is 4, or m is 4, n is 3. So there's actually quite a lot of solutions here. There's if we're looking at the 3 and 4 this way around, there's plus plus, plus minus, minus plus, minus minus, that's 4 solutions. And then there's another 4 from choosing the other 2. So there's 8 solutions in total. And finally, the solutions I missed when I was originally doing this, it doesn't say anywhere, it says they're integers, doesn't say anywhere they can't be 0. So m is 5, n is 0, or m is minus 5, n is 0, or the other way around. And there's 1, 2, using plus and minus, 3, 4 solutions here to make 16 in total. Good. Question number 4. So quite a lot going on here. It's labelled these side lengths 2, so we'll do that as well. This t is the midpoint. There's a helicopter flying outside. I'm so sorry if you can hear that, and it's really annoying. I mean, it's really annoying me. But anyway, I hope it goes away soon. There's a 1 here because t is the midpoint, and of course there's a 1 here, which of course means this length is root 5, and we could just call these two angles alpha and alpha, just for the hell of it. We're looking for this length here, x. So okay, what can we do? Well, I drew a line from T down perpendicular to PU, because the reason that I did that was I said, well, okay, now I can say these two triangles are identical, right? Because they have the same angle here, they both share this side root 5, and they both have right angles here, so these are congruent, which means this length is of course 1. That helicopter is really just not going away, so whatever. And this length from here just to here is 2. So okay, good. What can I do now? Well, I can draw a line from T to U, and this is the hardest bit of the question, but what you can say is these two triangles are also congruent, because they share a side length here, 1 and 1, they share a whole side here, and they also have a 90-degree angle in them. So by RHS, these are congruent. So if this length is x, so is this one. And you've got some more work to do here, but if you eventually angle chase a little bit, this is 90, so this is 90 minus alpha. We've already discussed that these two triangles are congruent, so this is 90 minus alpha, which makes each of these lengths, well, both of them are 180 minus this, but they're the same, right? So we just need to divide that by 2. 180 minus 2 of these divided by 2 is going to be this one, and if you do the algebra, that turns out to be alpha, and of course that means that this triangle is similar to the two triangles we've been looking at before, but of course we can just say here that the opposite divided by the adjacent of the original triangle is 1 over 2, so if this is similar, that the ratio between this and this also needs to be 1 over 2. This is only 1, so this is therefore a half. A half over 1 is a half, which is the same as this 1 over 2, which is a half. You could also think about scale factors or whatever, but you get x as a half. I thought I would also show, though, a much quicker way of doing this. If you allow yourself to use a bit of A-level maths, you can do this question very quickly by simply, you get back to this point, but then you simply say, well, this angle is 2 alpha, because it's alternates to these two with a z shape here, so 2 alpha here, 2 alpha there. Now, you know that tan of alpha is 1 over 2, opposite over adjacent, and of course you have a formula for tan 2 alpha with connecting tan alpha to tan 2 alpha, which is this, but you know tan alpha is a half, so 2 times a half is 1, half squared is a quarter, 1 minus that is 3/4, 1 over 3/4 is 4/3. So tan of 2 alpha is 4/3, but remember, that still equals opposite over adjacent. So if I write this a bit weird, if I write it as just halve both numbers, 2 over 1.5, here is 2 alpha, tan of 2 alpha is opposite over adjacent, 2 over 1.5, that means that's 1.5, which means that's a half. This is, I mean, I might just have to throw away this entire video if the noise is too loud. I really apologize, but otherwise we'll just see how it goes. If it's fine and you can't hear any of that, then we can just play it and you'll feel like I'm complaining about nothing, but trust me, the noise is really loud. It's actually just gone away as I say that. Hopefully it won't come back. Okay, so some simultaneous equations here. As soon as you see this, you do this. That should just be automatic, absolutely automatic. We can write down the second equation like this, and then what we can do is we can do this one divided by this one. But I can only do that if I make a note that a minus b, if a minus b is 0, then we're dividing by 0, so just make a note that I need to check this later. But for now, okay, I'll do this divided by this and cancel those two out. I'll cross multiply. Not really sure where I'm going with this, but if I expand this out, everything turns out really nicely because you end up with this, and this does actually factorize. Right, it's a little bit hard to spot, but it factorizes into that, which means, of course, that either this is 0 or this is 0, and 3a equals b, or a equals b over 3. Actually, that one comes from there, and this one comes from there. Okay, and so actually, we now have 3 things to check. We have this, and we have a equals b to check as well. So let's check all 3 of those. This one goes away quite quickly, because as soon as you do this, you notice that the first one, this becomes 0, and of course, something times 0 can't be 4. So there are, and likewise for the second one, so there are no solutions here. So it was good that we checked this, and you should always make a habit of doing that. In this case, it didn't actually matter. Now a equals 3b, so replace every a you see with a 3b. That makes 4b here. Just be careful, a squared is now 9b squared, so that gets replaced with a 9b squared. Do the same thing down here. Simplify both of those up. This just becomes 8b squared times that is 32b cubed, and this one becomes 20b cubed. Do this, take away that. This is 2.5, so this makes 4, take away that is 1.5. Divide by 12, 3 over 24 is the same as an eighth. Cube roots, and you get b as a half. Put it back into here, times it by 3, a is 3 over 2. Exactly the same thing over here, except what you could do actually is you can times both of these by 3, and then you actually have not only not have to deal with fractions, but you actually have a very similar process to this. All that's different is you actually have a couple of minuses in here because the b's come second, and yeah. So okay, we'll do the same thing, simplify both of those, do this, take away minus means an add, so we get this, divide by minus 12, cube root makes a minus half, and then put it back into here to make b as minus 3/4, or sorry, 3 over 2, and those will be our 2 solutions, and there are no solutions from here. Okay, the last question then. So this is actually a bit of spoilers, but it doesn't matter too much. What I decided to do first is just try this game here. So just place tiles down, see what the best you can do is. I tried to do it as methodically as I could, and I found that I could do every single place except for 2 of the dots on either side to make 4 dots in total, and that makes 36 tiles in total. And that I sort of felt was basically the best that I could do. I couldn't see, one of the things that's nice about this is it's completely symmetrical. And symmetrical solutions, either side of this kind of staircase, symmetrical solutions are often the most optimum. And I also tried doing that game, where you slide things around to try and slide them and get a more accurate thing and try and create a gap of 2, but I couldn't do it. So I was fairly happy this was the most, but of course I had to prove it. And I didn't really know how to prove it. I thought about it for a while and decided that if I was in the real exam, I just wouldn't have been able to prove this. So I used the mark scheme, and the mark scheme very helpfully provided the picture like this. And why is this helpful? Well, when you place down a tile on here, a tile needs to take up a black and a white space, or a light and a dark space, right? No matter where you put it, vertically or horizontally, it takes up a light and a dark, right? So what you do is you say, okay, well, let's just tile this here and this here. And now we've got 2 identical kind of halves here, except the top half has way too many light squares, and the bottom half has way too many dark squares. So let's actually count them up. Up here we've got 16 dark and 20 light squares. Now, because when you place down a tile, you take up exactly 1 light and 1 dark square every time, the absolute best you can do when you're tiling this top section is you'll miss at least 4 light squares. That's the absolute best you can do. Because you can put 16 tiles down to take up the 16 dark. That will take up 16 light, but you'll miss 4 squares. And likewise down here, count them up, is the exact opposite situation. So you'll miss another 4 squares. So you'll miss 8 squares in total, and you'll be much worse than what I did over here. But of course, that's because over here I tiled the first 2 like this, whereas over here I did this. So let's change that. Let's now tile them like this. And actually what I'm going to do is I'm also going to tile these 2 very obvious spaces that I can basically only do like this. And we see now we've got a very symmetrical situation. A few more light here than dark, and vice versa here, but it's not as bad. It's only 16 dark, 18 light, which means you'll only miss 2 squares at best. And here you'll only miss 2 squares at best as well. And so the absolute best you can do is miss 2 squares up here, 2 squares down here. And here's my example of that happening, and so therefore we can't do any better, and the optimum answer is 36 tiles. Okay, so that's the entire paper. Thank you so much for watching, and I will see you next time.